In this video, we're going to do a little bit of laboratory math. We're going to calculate solutions and magnification. As I look at it, our first part is percent, and that is parts per 100, parts divided by 100. So if I want to do 7% of 8, I want to write 7, and then you can do fractions, although I particularly hate those, of 8. So I'm going to translate that to then decimal form, and I'm going to say 0.07, which is 7 divided by 100 of 8. And that equals 0.56. So 0.56 is 7% of 8. Now, you can write the 0 in the front. You normally don't. That's your preference. Or I normally do, to be perfectly honest. So now if I want to take a look at 70% of 8, I would write my 70% as 0.7 times 8. And that's going to be 10 times more, is 5.6. So now 70% of 8 is 5.6. So percentage is basic. Moles, molarity, is moles per liter. And it's one of the major solutions that we always have to be concerned with osmolarity and things like that. So we're normally not going to make up an entire liter. So when we do this, we want to still use the same formula. We're just going to have to remember that our volume is in liters. So the first thing I put down is molarity. The molarity that's desired, times our gram formula mass or formula mass, whatever you want to put that as, and times our volume. And now remember, our volume is in liters, and so I'm going to write a little L in there so that if I end up with a decimal number for that, it's going to be in mLs. So as an example, I'm going to use a laboratory solution that's very common. I'm going to make 100 mLs of 2.3 molar sucrose. Of course, that's our typical cryoprotectant for immuno work and things like that. And so let's see what that takes. So if I'm going to do grams equals, molarity is 2.3, taking that from the formula, times a gram formula mass. And the gram formula mass of sucrose is a lot, of C12H22O11. So we have 342, and you can say the 0.3. Sometimes that's overdoing it. You know, significant figures get in the way sometimes, but so it's doesn't hurt to be as accurate as possible. And we're going to do that in our volume in liters, and we're only making 100 mLs, and so that 100 mLs is 0.1, and that's 100 mLs part of a liter. So our grams are going to equal the 2.3 times the gram formula mass, 342, times 0.1 for our 100 mLs. And so when I figure that out, it turns out to be I need 78.7 grams of sucrose into 100 mLs of our solution, and that's going to make 2.3 molar sucrose. Of course, now sometimes when you work in a lab, somebody forgot to order something, and so you don't always have enough. And so we would like 78.7 grams for our 100 mLs of 2.3 molar, but I only have 70 grams. But yet I have to maintain the 2.3 molar concentration because that's the functional aspect of it. I'm just not going to have as much as I wanted. So I have to change my volume to make that. So now we're going to solve the same thing, only we're going to solve for the volume. And when I do that, and of course with a little bit of algebra, it doesn't take a lot, but just pay attention. I'm going to have my grams is going to be divided by the molarity times the gram formula mass. So when I take that and calculate it, the volume that I'm going to be able to make is not going to be the 100 mLs. It's 70 divided by the gram formula mass times the molarity, and that turns out to be 0.088. Now we have to remember, and 99, we have to remember that that is in liters. And so when we get right down to it, we should just say that would probably be rounded off to just 89 mLs. You know, I got carried away with, 9 nines, and really that doesn't work. You're not going to measure that level of accuracy. So we're just going to round that off and say 89 grams into, or 89 mLs, excuse me, for the 70 grams. Now when we do stock dilutions, say that you have stock in the refrigerator and you want to make up a smaller volume. And for this example, I use the C1V1 equals C2V2. I want 300 mLs of 4% formaldehyde, and generally the solution comes in a stock concentration of 16%. So I have, or I'm using 16%. So I need to know how much 16% of formaldehyde I need to make 300 mLs of 4%. So I usually do the C1 as what I am starting with, and that's the higher, the stock concentration that I have, and that's 16, times V1, and that is my unknown. I don't know how much stock I need to make the 300 mLs of 4%. So I'm going to just put a little question mark in there. Now that equals the other side of our equation. The 4% concentration is our C2 times the volume is 300. So that turns out to be then 16, and I'll just put V1 equals 1200. So the V1 equals 75 mLs. So with the 75 mLs of 16% formaldehyde stock in a total volume of 300 mLs will give me a 4% formaldehyde. Now, just like we had in the last example, somebody forgot to order something, and instead of having 75 mLs, I'm going to end up with, I don't know, I might as well use the number that I've been coming up with. So let's say I only have 70 mLs. That seems to be a common number today. So now, with only 70 mLs, I know I can't make up 300 mLs of 4%. So how much can I make up? And so now I'm going to solve the same equation, only now I'm going to solve it for V2. Our C1 is 16%. Our V1 is going to be the 70 mLs. Before we didn't know the V1, but now we do, because that's all we have, and we're going to use all of that. And we still have desired 4% for our concentration of 2, and now we're going to solve for V2. That's our unknown. So we're going to do the exact same thing, just a little bit backwards, and we end up with 1120 divided by 4 equals 280 mLs. And so now, instead of 300 mLs of 4%, we're going to have 280 mLs of 4%. And this happens a lot because you don't always have all of what you need. So now we're going to do Karnofsky's, and this is a beautiful fixative, and it's nice from a calculation point of view because we're going to use the molarity, we're going to use the percentage, and we're going to use the concentration volume formula for preparation of the entire solution. So we want 250 mLs of 1.5% glutaraldehyde, 2.5% paraformaldehyde, and 0.1 molar phosphate buffer. We have our monobasic and dibasic phosphate buffer, and that's granular, so we'll be able to have as much as we want. And the PO4 just indicates the phosphate. And then I also have paraformaldehyde, and that is in prils. That also comes in a granular form. I prefer to use the prils. And so now I have to figure out my glutaraldehyde, and again the prils. So the glutaraldehyde is my concentration volume formula, and I have a stock of 50%. So that's in a bottle, and it's EM grade glutaraldehyde. And this is the one where we have to be careful because we also offer ampules, and many labs do use the ampules. And so if you have an ampule versus the stock 50% glutaraldehyde, it's a good idea to use that as your limitation and indication of your volume, because you don't want to open an ampule and leave it some left over. So if I have a 10 ml ampule of 25%, I'm going to figure out what the volume I can make of my solution using all of that glutaraldehyde. So when I do that, I'm just going to use my C1V1 equals C2V2. I find this formula to be ubiquitous. You're using it all the time. And so my concentration of my V1 is 25%, and the volume of it is 10 mLs. And again, with these calculations, if you use the same units, you don't have to put it in terms of liters or percents and things like that. So now my concentration that I want is 1.5, and my V2 now is the unknown. So when I calculate that, I get 250 divided by 1.5 times V2. So V2 then equals 166.7 mLs. Now, oftentimes, of course, you're going to round that off to 168 mLs, and if you're accurate enough, you can get that. So that would be if you have a 10 ml ampule of 25%. You can't make up 250 mLs, you have to make up 168 mLs. But we have the 50% stock, so we're going to use that. So we're still going to use the 250 mLs because we have the 50% stock. It's not to worry. So the first thing we want to do, though, is figure out our concentration for the buffer, because generally speaking, when you're making Karnofsky's, it goes into the paraformaldehyde goes into solution easier with other ions. So we're going to use a 1.25, a 1 to 2.5 ratio of monobasic to dibasic. And what that does is puts the buffer in the same pH range, about approximately 7.2. So we want to figure out what are the different parts. And what I like to do is just take the total volume and divide it by the total number of parts. And so I have 250 mLs divided by 3.5 is going to give me the number of 71.4 is the one part. Now the 0.4 there is questionable. Sometimes you're going to round that off, and we'll take care of that in a little bit. So our monobasic has grams equals, And again, our calculation for molarity is the desired molarity times the gram formula mass is 138 for monobasic times our 1 part, because the monobasic was a 1 to 2.5. So our 2.5 is going to be dibasic. And so that comes out to be, remember that we want to put that in liters. So 0.071. If you do the 4, you can round that off. It doesn't hurt when you have calculators, but sometimes those small numbers get in the way. And so the grams for our monobasic are 0.985. Of course, you can, depending on what type of a scale you use, you might just go with 1 gram. Certainly there's leeway when you're doing most of these solutions. For our dibasic, the grams equal our same molarity, 0.1, times the gram formula mass, and for the gram formula mass for the dibasic is 288. And be sure to add in the hydrations when you calculate that if it's not written on the bottle. And now we had the 1 part, but now we want 2.5 of that. So I need to multiply the 2.5 times 1, and that 1 part was a 71.4, and that then comes out to 178.6. And we can see the 0.4 and the 0.6, you can just get rid of the 0.4 and make that, rather than 178, just make it 179. It's that much easier. You're not going to be probably that accurate anyway. So now when we come out to it, the grams equal 5.14 grams. And so that's what we're going to do. We'll add that to water, get that boiling, and then we'll add our performaldehyde. And I have another video that shows the actual process if you'd like to watch that. So now let's take a look and calculate our paraformaldehyde. And again, that's a basic percentage solution. Remember how we would write 2 and 0.5% is 0.025. And just be careful you don't write 25, otherwise it's going to be quite concentrated. And our volume that we have is still the 250 mLs. So we end up with 6.25 grams. And so that is for our paraformaldehyde. And our dibasic, we have 5.14 grams and 0.985 grams, or 1 gram of our monobasic. And so that's what we need for our buffers. So now, and the paraformaldehyde, let's take a look at our glutaraldehyde. Again, we covered before, if you have a vial, a 10 ml vial of a certain percentage, how to do that and put that volume into the rest of the equations. But now we're using our stock 50% glutaraldehyde. And so let's take a look at what we have. Our concentration 1 is 50%. Our volume 1 is our unknown. And so that's what we have to figure out. How much are we going to use for our 250 mLs? Our concentration is just 1.5%. And this is a Karnofsky's for plants, which has a higher concentration of paraformaldehyde versus glutaraldehyde, since they don't have as much protein for the glutaraldehyde to be reactive with. And so when we do that, we end up with 7.5 mLs of our glutaraldehyde, 50%. And so that will give us then our 250 mLs of 1.5% glutaraldehyde. Now we're going to take a look at magnification. Generally speaking, we're looking at the scale bar or micron marker at the bottom of the image. And what I've done is I've measured that, and the length of that with a ruler is 30 millimeters. And I can put that into decimal form or scientific notation, which is generally easier to work with. The indicated is 2 microns. Now that's 10 to the minus 6. If we count over, it's again easier to use scientific notation. And in order to do this, I take the measured distance, the 30 millimeters, divided by the indicated, which is 2 times 10 to the minus 6. And if I divide 3 10 to the minus 2 by 2 to 10 to the minus 6, I end up with 1.5 times 10 to the 4, and that's 15,000 times magnification. Thank you very much.